Hello, it's Keith here, and this is lesson 3 of the basic series of my assembly programming tutorials. In this series we go over a variety of general concepts and terms that you might come across when you're doing assembly programming. We don't go into the details of any specific CPU programming language. I do have tutorials on Z80, 6502, 68000 and so on. That's not what we do here. Here we're just discussing the background concepts and giving you a bit of a general background information so that when you look at those series you've maybe got some prior information if you're just starting out. Now today we're looking at more details about the CPU. We've looked at the basics like registers and things, but there are a few weird concepts that some of these processors instruction sets have that we need to know about before we start programming them, otherwise we might find things a little bit confusing. So we're going to go over a variety today. Now the important thing with today is if you find you're getting lost and you don't really understand bits of it, don't worry about it and just ignore the bits you don't understand, because as I say, depending on the processor, the concept may not be relevant to the system you end up programming. So let's make a start. So the first concept we're going to discuss is resets and traps. Now these relate to a variety of processors. A reset is a big thing on the Z80, and traps exist on a lot of the processors these days. These are basically memory addresses within the CPU that are allocated, they're fixed memory addresses, and these are executed under certain circumstances. For example, the very common one on the Z80 is reset 0, which is literally when the CPU starts up. The memory address 0 will be executed, and whatever happens to be there at that time will be what starts up your computer. Now maybe that's your cartridge on your Sega Master System, or maybe that's your firmware on your Amstrad CPC, but something there will do the job of starting things up. Another one is the interrupt handler. Now on the Z80 again, there is an interrupt that was usually on VBlank, which is when the screen is completely redrawn, and we can put our own program code in that memory address, and that will actually cause a jump to our own code when the screen is completely drawn, and we can do clever things during that time. Maybe we need to load in some new graphics for the next drawing of the screen or something like that, or update our sound. Good way of making your sound at constant speed. Now on the 68000 systems we also have traps and we have interrupts and things, but the traps also allow for very clever things like debugging. We actually have some debugging traps. Now if you're creating cartridges or if you've got total control of the system, you will probably need to put some kind of traps on your 68000 code, a default set even if you don't want to use them, or resets on your Z80 based systems like your Sega Master System. On if you look at a Neo Geo ROM or a Genesis ROM, a Mega Drive ROM, you will see there's a big block of traps, and some of those have specific purposes, and you will have to put in usually template code to handle those accordingly. So basically these resets and traps, also interrupts on the 8086 are the same kind of concept. They will do a variety of things. They can be for error checking, interrupts and things like that, and the other thing we can do with them is we can execute them at our own request, and also we can use these interrupts and resets to write our own commands. So we can put our own code at specific unused interrupts or resets or traps depending on the processor and make those do things that we want. They are also often used for operating system calls on the Z80 Amstrad CPC, MSX, and also the 8086 DOS with the interrupts. These actually have specific operating system functions, and we'll have some kind of manual somewhere that tells us what these interrupts do, what the parameters we pass to them do, and we can use these for all kinds of things like maybe drawing characters to the screen, maybe calling to change the graphics mode. It really depends on the system, and you need to check the documentation to understand what the actual things that those interrupts, traps or resets, just depending on the terminology of the processor, will actually do. A bit of a weird concept there. Another concept which really isn't relevant to your 8-bit processors is something known as privilege modes. Now, as processors became more and more advanced, the concept of multiple tasks running on the processor at the same time became a more serious thing. And it became more important that a simple task like your running program can't negatively affect the resources used by the more important tasks like the disk operating system, because you don't want your running program to corrupt your disk, and you don't want your running program to crash the underlying operating system unintentionally. So this concept of privilege modes came into place, and this was where you would maybe have different resources split out to two separate parts of the system. It depends on the processor. Maybe you have a different set of registers for the running program and for the operating system, or maybe it's simply that some commands aren't available to your normal running program that are available to the operating system. It really depends on the kind of processor you're programming. As I say, this isn't really relevant to 8-bit processors at all, and it depends on the 16-bit processor. Again, it's something you'd have to look into when you decide what the particular processor you're interested in. Now, if you're interested in a processor that's based on the 6502 type of processing model, then what you will want to know about is the 0 page, which is also on some systems known as the direct page. Now, these processors had very few registers. A system like the Z80 had quite a lot of registers, but processors that were based on the 6800 type processing model before the 16-bit 68000, that is, had very few registers. And this meant there wasn't many cases where you'd be able to write a program without accessing memory to get and store temporary values and things like that. And what they came up with as a solution to this is what's known as the 0 page, which was later renamed to the direct page. The concept of the 0 page was basically that if we have an address will be 16 bits, that's 2 bytes, and we will also have some kind of command which is an extra byte, so all our commands will end up 3 bytes. This makes our program big and a bit slow. So rather than using 2 bytes to specify an address, they just use 1 single byte. Now, the real address, the 16-bit address, really did have 2 bytes, but they made the top byte always 0. So this would always address the first 256 bytes of the system's memory. And this meant the commands only used 2 bytes, 1 byte for the command and 1 byte for the 0 page memory address. And it meant the commands were smaller, and because they were smaller, they were faster. And so this was referred to as the 0 page because the top byte of the 16-bit address was always 0. However, with the later, more advanced processors like the 65816 and the 6809, these gave more flexibility and allowed the 0 page to be anywhere within the first 64 kilobytes of memory. And so because it no longer had a top byte of 0, it was renamed from the 0 page to the direct page, but the function is exactly the same. Now, if you're struggling with the 6502, and I did, because for me, I was used to the Z80 with lots of registers. I didn't have my registers on the 6502, and I couldn't quite get my head around that. What I suggest you do is you think of the 0 page as a big bank of registers and use it like that. Allocate certain entries in the 0 page to certain purposes as temporary variables, as pairs, and that can be used in commands that you would need 16-bit memory addresses, things like that, and work with them that way. Now, one other thing that's worth very quickly mentioning here is that is exactly what the TMS 9900 does. That processor has almost no registers, and it actually has something known as a workspace, which is basically a 32-byte 0 page in effect. The way it works is identical, but that processor actually refers to those as registers. So that's just I do think that thinking of them as extra registers is a valid way of conceptualizing the 0 page when it comes to working with data in your processor. Okay. So that's the 0 page, which is definitely very much an 8-bit processor thing, although the 65816 was a partially 16-bit processor. Now, when processors became larger, and especially when they extended from one size to another, when a processor that originally had, say, a 16-bit address bus expanded to a 24-bit one, or one that had a 20-bit address bus expanded to 32 or something like that, this often caused quite serious problems. And the problem was, of course, that the processor's underlying hardware was designed to work around a smaller address range than was now capable. And the way that this was usually resolved was with some kind of extra registers, and the terminology wildly varies depending on the processor, but these are often referred to as something like segment registers or bank registers. And what this is if you imagine that there was an 8-bit processor, for example, the 6502 was an 8-bit processor, had a 16-bit address bus, but then this was expanded to a 24-bit address bus, well, you now have an extra 8 bits that you need to specify for your addresses. And the way this was done on that processor and on a lot of other processors that came across this problem, like the 8086 and the Easy80, was to have an extra byte register that was the top byte of all of the addresses that were specified in 16 bits. Now, this got around the problem, but it tends to make working in full 24-bit or for whatever the full address space of that processor is quite difficult, and it's a bit of a kludge when you compare the 8086, for example, the way it addresses its memory, to the 68000. They both are capable of addressing the same kind of address space, but the 68000 didn't have that backwards compatibility problem because it started effectively from scratch, whereas the 8086 was designed to work in the same way as the original 8080, and so it had the problem of segment registers, which was quite a pain. Now, one thing that you probably don't need to worry about too much when you start programming, but is something that's really going to help you out the earlier you are able to understand it with regards to writing more efficient code and just working out how to solve problems, is a concept which will vary wildly in its terminology, but I'm going to refer to it now as base pointer plus offset addressing. Now, when we need to read a parameter or write a parameter, often we will specify the memory address that we want to read from or write to as a register, but sometimes just a single register isn't so convenient with what we want to do. Sometimes we will want to specify the destination in two parts, and one of these will be a base pointer and one of these will be an offset. For example, our base pointer might be a 16-bit address register, and then our offset might be an 8-bit fixed value, for example 0 to 255 or minus 128 to plus 127, which is an offset from that original point. Now, this is used in a lot of different places, and the terminology does vary depending on the processor. On the 8086, it's called base pointer and offset, but on systems like the Z80 and the 6502, it's referred to as index registers. There's special registers that do this job, and you're probably thinking, well, what does this mean? Why would I want to use this? And the time that this really came into play for me is when I started writing games that had two players. You've got a piece of code that handles your player, but then you want to run it on a second player, and in memory somewhere you've probably got a block of memory that defines the current position, the current sprite, the lives left of the player. And what you do is you point your base pointer or your index register, depending on the terminology, to the start of player one's memory block, and then the player handling code will have all of the offsets to the sprite number, the X position, the Y position, and the remaining lives specified as an offset from that base pointer. That piece of code can be run for player 1, and then when you want to do the same job for player 2, you just switch the base pointer, point to the data for player 2, and you run the exact same routine again. This means you can have one routine that does player 1, player 2, and maybe, depending on your program, all of the enemies as well, and it's just the base pointer is being pointed to a different block of data, and the code is looking at different offsets from that original base pointer to do the job. As I say, again, it's not something you probably need to worry about when you're literally getting started, but as you start trying to think of more advanced games you want to make or more advanced programs and trying to think how to do things efficiently, there's no realistic way you're going to be able to create a separate module to handle all of the movements and all the sprite drawing for all of the kinds of enemy and player in your game. And what you will probably want to try and do is write one common piece of code that can handle all of those different object types or players or enemies or whatever your game requires. And as I say, this is how I always do it, and I think this is the best way of starting to write code that is more flexible. Now, you might hear addresses referred to in two different ways, absolute and relative, and when you're getting started, this probably will be a bit of a mystery to you, although if you think about the words, it will start to become a bit clearer. Now, when you've got a processor with a 16-bit address bus, a full address can be specified as a 16-bit value, and this will be an absolute value. So for example, if we jump to a memory address 3000, that is the absolute address 3000, and that's where our execution will carry on from. But there will be times where we don't want to specify an absolute address. We might want to specify the address to jump to relative to the current position in the code. So instead of saying jump to address 3000, you might want to say jump 5 bytes down in the code. Well, why would you want to do that? Well, there's two reasons. Firstly, again, a 16-bit address takes 2 bytes, and that means our jump command is probably going to be 3 bytes. That's a bit big. If we specify a relative offset of minus 128 to plus 127, that's a single byte. So our jump relative command will only be 2 bytes. We've saved 1 byte, and that makes our program smaller and therefore faster. So relative jumps allow for smaller code, and that's going to be a big benefit on our 8-bit systems. But another benefit is these allow for something known as relocatable code. Now, relocatable code is where the code doesn't care where in memory it's been put. Now, if we design our program to only run from memory address 3000, that might be fine at one point, but what if we need that memory address for something else? Maybe there's another task that needs that, and we want to move that code to a different memory address and run it at that different memory address. If we're using absolute addresses, that won't work, but if all our addresses are relative, that's going to work just fine. It's worth noting that code that runs at fixed memory addresses is really a thing for the 8-bit world. With the 16-bit world and later, things became far more relative, and on the 68,000 type processors, typically all code is going to be relative. It's not entirely true, but as a general rule, as soon as you've got an operating system on a 16-bit processor, everything's probably being done relatively because you've probably got some memory management working things out for you. Now, on most processors, you'll have different commands to specify the kind of jump, or if you're on a later 16-bit or 32-bit processor, it might be the assembler works it out for you, and you'll need to check the documentation for the full details there. But at this point, just remember the difference between an absolute and a relative address for when you want to choose which kind of command you want to use. Okay, so that's a variety of different concepts that you may come across on different kinds of processor, just depending on what processor you've chosen and what you're looking to do. Now, what we're going to discuss next is a few more technical concepts regarding processors that possibly you don't entirely need, but I wanted to try and give you all of the terminology you might hear thrown around out there that you really don't know what it means. And I'm going to explain some of them just so when you hear them, you will know, I vaguely know what that means, and I know I don't need to worry about it is probably the truth, and that is definitely the truth with RISC and CISC CPUs. These are terms that are used to classify processors, but they really don't have any particular relevance to the programmer. Now, RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. Well, what's a reduced and what's a complex? Honestly, it doesn't make a lot of sense anymore. These terms were allocated to processors based on their release dates. So we now have a baffling world where the Z80 is considered a complex CPU, whereas the massively more powerful and flexible ARM is considered a RISC CPU. It doesn't make a lot of sense, but one thing that I think is probably quite important for you to understand is if you are programming a processor that is considered to be a RISC processor, which is the ARM RISC-V, MIPS, PowerPC and SH2, you might find that you are unable to find instructions that you would expect to find, or you might find things are taking more commands than you would really expect, and you would think, well, why is that? And that's probably the reason. The reason is probably that they have simplified the instruction set, and that's why it's a reduced instruction set computer, to make the instruction set more easy for the processors to execute, and therefore it's able to run it more quickly. And that's why on the RISC-V, for example, you can't push and pop multiple registers at the same time, and that's also why, which we're going to discuss next, some processors are limited to the load and store architecture. Now, what is the load and store architecture? Well, this is a thing of the RISC processors. On a system like the 68,000 or the 8086, we have an architecture known as the register and memory architecture, and this allows for mathematical operations to work with register and values within memory. However, the load and store architecture, which is more popular with the RISC processors like MIPS, RISC-V and ARM, these tend to split the commands up into two parts: your read from memory and your write to memory commands, and your commands that do mathematical operations and other kinds of calculation. And so on these RISC processors, you will often see this kind of clunky, in some ways, set of commands: a command to load a value in, a command to do a calculation, and a command to write the value back. Whereas on the CISC processors, you would have maybe seen those as a single command or maybe two commands. And again, you might be thinking, well, why is my super advanced RISC-V processor not able to do this when the 68,000 could? And again, it's all about, they've reduced the complexity of the instruction set to make the processor more simple and therefore more quick. So again, just something I wanted to discuss, and while you don't need to remember the term load and store architecture, I think it does help to understand why you might be looking at the instruction set and going, well, why is this so limited? It's all to do with this RISC concept. Now, a concept you won't need to really worry about unless you're looking at 32-bit RISC processing is the instruction pipeline. Now, as processors became more and more complicated, they started to look for ways to make them more efficient. And one of the things that they did to make them more efficient was they started processing multiple commands at the same time. Well, what does this mean? Well, this means the processor will actually be loading in multiple commands at the same time, and it will be thinking about how it's going to deal with future commands when it's not yet processed the first one. For example, we've got an imaginary processor here with a three-stage pipeline: a fetch stage where a value is read from the memory, and you can see that represented just here. This is our fetch stage with bits of paper being lifted up from in trays. A decode stage where the command is being looked at under a microscope, and an execute stage where the command is being passed to the Chibico character here, who is the master of the processor. So in this case, the 3 stages are all dealing with jobs that will need to be done before the command can actually be executed. So it's being split up into 3 stages. And here in this example, the 3 commands being processed are a load command, an add command, and a store command. So at this stage, the load is at the front of the queue. So the value 3 will be loaded into R1. The next command that will get to the front of the queue is adding 1 to that value in R1. And then the third will be storing R1 to the memory address in R2. Now this is just an imaginary instruction set. This isn't a real processor, but this is the kind of thing the processor will do. The idea of this, of course, is if we are working on 3 commands at the same time, we can hopefully increase our speed. This, however, does cause some problems, because this is all very well and good when we've got 3 consecutive commands like load, add, and then store. But what about if we come across a jump command? Because the following 2 commands shouldn't be executed, because that jump command will change the position of execution in our program, and we do not want to load a different value into R1 after that jump. So what does this mean? Well, this means that the instruction pipeline will need to be flushed. So the jump command occurs here, but then the load and the add command, they don't want to happen. So the processor has to flush the pipeline and wipe those out. Well, what does problems this cause? Well, simply that we've wasted some processing power, because now commands that had already been loaded and were in the process of being decoded, well, now they're gone. So we're going to have to now refill the pipeline with new commands from the destination of that jump, which slows things down. Now, this is the way that some processors work, like the ARM and the RISC-V work in this way. But other processors have come up with what I think is a bit of a radical solution to this delay, and they have a concept known as delay slots. Now what this means in some cases is when a command that should mean a total flush of the queue, like a jump, is encountered, like this jump here, rather than all of the commands in the queue being flushed, the command immediately following the jump, this load here, is in an area referred to as a delay slot. It's the slot immediately after the jump, and rather than being flushed, it's actually executed before, represented by that rather stretchy arm there, before the jump actually happens. You heard me correctly. The command after the jump occurs before the jump happens, and this is referred to as a delay slot. Now, the second command in the queue in this example would still be flushed, and the reason that this is being done is simply to reduce the amount of data lost during this pipeline flush after the jump. Now it might be too confusing for us to have to think that our command after our jump is going to be executed anyway, and the simplest solution is to put a no operation command, a NOP command, and this will effectively do nothing, and that will mean that the extra command that we don't want to be run won't be run. But if we can get our head around this rather strange programming method of delay slots, it does help us out. Now this issue of delay slots is sometimes referred to as a control hazard. This is because the control flow isn't working in what you would expect to be the traditional way. Another delay issue on the MIPS processor particularly is what's known as a delayed load, and this is referred to as a data hazard. And this refers to when a command is performing a load and then a second command is trying to perform an action on the value that was just loaded. Now in some cases that load command may have not actually completed execution by the time that the next command comes along. So again, there may be some cases where a delay is needed there as well. Now as I say, this is all very specific to a particular processor, and it's not going to be something you need to worry about on any of the basic 16-bit or lower processors. This is only something for the 32-bit processors and really the RISC 32-bit processors, and not even all of those. So what you need to do is you need to check the documentation of the specific processor you're looking at. If you're on ARM or you're on RISC-V, you don't need to worry about this, but if you're on MIPS, if you're on SH2 or you're on PowerPC, you may need to worry about this kind of thing. So again, check your documentation. Anyway, that's all we're going to be covering today. Now, I apologize, there was a lot of technical terminology and things in there. We're going to go for something a bit more simple next time. I just wanted to go through all of the important terminology that I kind of struggled to understand in the early days with regards to processors. Next time, we're going to be doing something a bit more simple, and we're going to be discussing different kinds of number representation. That's going to be a lot more simple and also a lot more important, actually, because you will definitely need to know what decimal is, binary and hexadecimal, if you're going to program in assembly, whereas the stuff in today's today's lesson. I think it's interesting information that is stuff that I struggled with, but if you didn't understand the content of today's lesson, you're still probably going to be fine, certainly in the early days of the process you're programming. Anyway, I hope you've enjoyed what you've seen today. All the content is available on my website, so if you want to go and read through it again, please check it out. And if you want a printed copy of my tutorials, this lesson was actually based on the first chapter of my book. So if you want a printed copy, please go to Amazon and please consider buying my book. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching and goodbye.